In August 2012, more than 18 billion kilometers from Earth, a spacecraft the size of a small car detected something no human instrument had ever measured before. The numbers changed abruptly. Galactic radiation surged. Solar particles vanished. For the first time in history, humanity was touching the edge of the sun's influence. The spacecraft was Voyager 1. Launched in 1977 under the authority of NASA's Jet Propulsion Laboratory, Voyager was never designed to find the boundary of the solar system. Its mission was planetary exploration, Jupiter, Saturn, a grand tour of the outer giants. Yet gravity did what engines could not. After its final planetary flyby, Voyager continued outward, faster than any previous probe, carrying with it a suite of instruments built to measure magnetic fields, charged particles, and plasma waves. For decades, scientists had predicted that our solar system is enclosed within a vast magnetic bubble known as the heliosphere. This bubble is formed by the solar wind, a continuous stream of charged particles expelled by the sun at hundreds of kilometers per second. As that wind expands, it pushes against the interstellar medium, carving out a protective cavity in the galaxy. Inside this cavity, Earth is shielded from a significant fraction of high-energy galactic cosmic rays. Without that shielding, radiation levels would rise, atmospheric chemistry would shift. The conditions that allowed life to evolve might have unfolded differently, but until Voyager, the heliosphere was theoretical. Its outer boundary, the heliopause, existed only in mathematical models and simulations. Estimates placed it somewhere between 100 and 120 astronomical units from the Sun. No spacecraft had ever travelled that far. By the early 2000s, Voyager 1 was closing in. Its cameras had long since been powered down to conserve energy. What remained were instruments tuned to the invisible: magnetometers, cosmic ray detectors, plasma sensors. They were listening for a change in environment, a transition from solar dominance to galactic influence. Scientists expected a gradual shift, a slow blending of solar wind and interstellar plasma. What Voyager would ultimately find was sharper, stranger, structurally complex, because the edge of the solar system was not a simple boundary, it was a dynamic interface. And before Voyager could reach that final frontier, it would first encounter something else, an invisible shockwave where the solar wind itself breaks. That is where our journey truly begins. December 2004. Nearly 14 billion kilometers from Earth, Voyager 1 encountered a wall that no telescope could see. The data did not arrive as an image. It arrived as numbers. Subtle at first, then undeniable. Magnetic field strength rose sharply. The behavior of charged particles shifted. Anomalous cosmic rays intensified. Something in the environment had changed. For decades, heliophysicists at NASA's Jet Propulsion Laboratory had predicted the existence of a boundary called the termination shock. It was described in plasma physics models as the place where the solar wind, racing outward faster than the speed of sound in that medium, would be forced to slow abruptly under pressure from interstellar space. A shock wave, not of sound, but of charged particles and magnetic fields. Until that moment, it had only existed in theory. Voyager 1's plasma instrument had failed years earlier, leaving scientists partially blind to direct solar wind speed. What remained were magnetometers and cosmic ray detectors. The evidence they provided was indirect, but it converged. The solar wind had transitioned from supersonic to subsonic flow. The spacecraft had crossed the termination shock at approximately 94 astronomical units from the Sun. This was not the edge of the solar system. It was the beginning of its final layer. The crossing carried profound implications. It confirmed that the Sun's influence does not fade gradually into space. It ends in compression, in turbulence, in a measurable shock front shaped by forces beyond our star. Then, in August 2007, Voyager 2 crossed the same boundary at just 84 astronomical units, 10 astronomical units closer to the Sun. The discrepancy was not an error. It was revelation. The heliosphere was not symmetrical. It was compressed in the south and extended in the north. The interstellar magnetic field was pushing unevenly against our stellar bubble, distorting it like a hand pressing against a balloon. For the first time, humanity possessed stereo measurements of the Sun's outer frontier. The solar system was not isolated. It was embedded within galactic forces strong enough to reshape its boundaries. Beyond the termination shock lay a region scientists called the Helios sheath, a turbulent expanse where slowed solar wind would pile up against interstellar space. Models predicted it would be thick, gradual, structurally simple. Voyager was about to prove otherwise, because what waited ahead was not calm plasma drifting toward a boundary. It was something far more chaotic and far less predictable. By 2008, Voyager 1 was more than 100 astronomical units from the Sun, drifting through a region no spacecraft had ever sampled. Scientists expected this zone, the Helios sheath, to be a slowing river of plasma. Instead, it behaved like a storm. The instruments at NASA's Jet Propulsion Laboratory began transmitting data that defied the clean diagrams of heliophysics textbooks. Magnetic field readings fluctuated rapidly. Directions shifted over short distances. Particle intensities pulsed irregularly. The Helios sheath was not smooth. It was structured. Physicist Merav Ofer and her colleagues proposed an explanation grounded in magnetohydrodynamics. The Sun's magnetic field reverses polarity every 11 years. As the solar wind carries these alternating magnetic sectors outward, they compress and fold as they approach the outer boundary. In 2009 and 2010, Voyager's magnetometer revealed that those sectors were fragmenting into vast magnetic islands, each roughly 160 million kilometers across. A magnetic foam. This was the central discovery. The Helios sheath was not a laminar buffer between the Sun and the galaxy. It was a frothing sea of disconnected magnetic bubbles, constantly merging and separating. Plasma did not glide toward the heliopause. It churned. The implications were immediate. For decades, models assumed that the heliosphere deflected galactic cosmic rays with a coherent magnetic shield. A smooth barrier would bend incoming radiation outward. But a foam behaves differently. Charged particles can scatter between bubbles, become temporarily trapped, or leak inward through weak magnetic seams. Radiation shielding was more chaotic than expected. For Earth, the heliosphere reduces the flux of high-energy galactic particles that would otherwise penetrate the inner solar system. If that shield is porous, even slightly, the radiation environment of planets can vary over time. That affects atmospheric chemistry, climate stability, long-term biological exposure. Voyager was not simply mapping a boundary, it was measuring the architecture of our protective cocoon. There was another surprise. Pressure readings suggested that disturbances from solar eruptions years earlier were still propagating outward, compressing regions of the Helios sheath long after their origin. The outer solar system was not static. It responded to events at the Sun with delays measured in years. The heliosphere was breathing. By 2011, Voyager 1 had traveled deep into this magnetic turbulence. The cosmic ray detectors began recording subtle increases in galactic particle intensity. Not dramatic, not yet decisive, but persistent. The outer frontier was approaching, and the transition, when it came, would not unfold quietly. It would arrive as a sudden surge from the galaxy itself. July 28, 2012. Without warning, the numbers surged. Voyager 1's cosmic ray detectors recorded a sharp and sustained increase in high-energy galactic particles. At the same time, the intensity of lower-energy particles originating from the Sun dropped precipitously. The change was not gradual. It was abrupt. For scientists at NASA's Jet Propulsion Laboratory, this was the signal they had waited decades to see. The spacecraft was now more than 121 astronomical units from the Sun, over 18 billion kilometers away. Communication delays approached 17 hours one way. Yet the data, when finally received on Earth, was unmistakable. Galactic cosmic ray flux had risen to levels never before measured by a human instrument. Statistically, the increase exceeded normal fluctuation ranges by a wide margin. The particle environment had shifted into a new regime. It appeared that Voyager 1 had crossed the heliopause. The heliopause is the theoretical outer boundary of the heliosphere, the point where the outward pressure of the solar wind is balanced by the interstellar medium. Beyond it lies true interstellar space, dominated not by our Sun, but by the galaxy. If this interpretation was correct, humanity had just entered interstellar space for the first time. But then, something unexpected happened. On August 1st, The particle readings reversed. Solar particles briefly reappeared. Galactic intensity dropped. The boundary seemed to move. On August 5th, the surge returned, stronger and sustained. The transition was not a single crossing. It was a stuttering oscillation. Voyager appeared to be moving in and out of a fluctuating frontier, as if the boundary itself were rippling in response to pressure changes between star and galaxy. This was not the clean, spherical edge predicted by earlier models. It was dynamic, thin, responsive. By late August 2012, the solar particles had fallen to near zero and remained there. Galactic cosmic rays dominated the environment consistently. The evidence for crossing was now compelling. In September 2013, NASA formally announced that Voyager 1 had entered interstellar space in August 2012. Yet one critical measurement remained puzzling. The magnetic field direction had not rotated as expected. The Sun's magnetic orientation persisted even as galactic particles flooded in. The spacecraft had crossed into a new particle regime, but not into a clearly new magnetic geometry. The edge of the solar system was not behaving like a wall. It was behaving like an interface. And to understand that interface, scientists would have to confront a discovery even more complex than the crossing itself, because what Voyager had entered was not simply interstellar space. It was something in between. August 2012 did not deliver a clean farewell from the Sun. It delivered a paradox. Voyager 1 was now immersed in a particle environment dominated by galactic cosmic rays. Solar wind particles had nearly vanished. By every particle-based definition, the spacecraft had crossed into interstellar space. NASA announced the transition in September 2013, citing the sustained shift in radiation levels first observed in August 2012. But one measurement refused to cooperate. The magnetometer, built under the direction of principal investigator Norman Ness, continued to report a magnetic field aligned with the Sun's spiral orientation. According to prevailing heliospheric models, crossing the heliopause should have produced a noticeable rotation in magnetic direction, an unmistakable shift from solar to interstellar alignment. It did not happen. The field strength increased, the particle regime changed, yet the magnetic geometry remained stubbornly solar. This inconsistency forced scientists to confront an unexpected reality. The boundary between the heliosphere and interstellar space was not a sharp discontinuity, it was a connected structure. Researchers analyzing the 2012 data proposed that Voyager had entered a transitional zone where magnetic field lines from the Sun were linking with those of the interstellar medium. These connections created open pathways, corridors along which particles could stream freely in both directions. Solar particles escaped outward, galactic particles streamed inward. The region was named the Magnetic Highway. It was narrow, less than 1 astronomical unit thick. On a journey spanning over 120 astronomical units, the transition layer amounted to less than 1% of the total distance from the Sun. Yet within that thin corridor, the physics of stellar boundaries became visible. Magnetic reconnection, where opposing magnetic lines snap and rejoin, may have been occurring at this interface. Such processes are known to release energy and accelerate particles on the Sun itself. Now, similar mechanisms appeared to shape the frontier between star and galaxy. The stakes were profound. If the heliopause allows particle exchange along connected magnetic structures, then the heliosphere is not a sealed shield. It is permeable. Its effectiveness as a radiation barrier depends on geometry, timing, and solar activity. This realization altered not only our understanding of the Sun's outer boundary, but of all stellar systems. Every star moving through the galaxy must negotiate with its environment. Each astrosphere may contain its own magnetic highways, its own dynamic interfaces where local and galactic forces intertwine. Voyager had not simply crossed into interstellar space, it had revealed how the crossing works. And even deeper into that interstellar medium, another measurement was beginning to rise, one that would confirm beyond doubt that the spacecraft had left the Sun's domain behind. The final proof would not come from particles alone, it would come from the sound of plasma itself. In April 2013, nearly 8 months after the Great Particle Surge, Voyager 1 heard something. It was not a sound in the human sense, it was a vibration in plasma, an oscillation in the thin gas between the stars. and it carried the final confirmation scientists had been waiting for. The trigger came from the Sun itself. In March 2012, months before the August boundary transition, a powerful coronal mass ejection erupted from the solar surface. The shock wave from that eruption travelled outward through the heliosphere at supersonic speeds. More than a year later, it reached Voyager 1. When the shock passed the spacecraft in April 2013, the plasma wave subsystem, led by principal investigator Donald Gurnett at the University of Iowa, detected high-frequency oscillations in the surrounding plasma. Those oscillations allowed scientists to calculate the electron density of the local environment. The result was decisive. The measured density was approximately 0.08 electrons per cubic centimetre, more than 40 times higher than the density typical of the heliosheath. Such values matched theoretical expectations for the interstellar medium. This was not inference from particle ratios. It was not indirect interpretation of magnetic geometry. It was a direct measurement of the density of interstellar plasma. With that single data set, the ambiguity narrowed dramatically. Voyager 1 was no longer inside the Sun's plasma environment. It was immersed in the galactic medium itself. The announcement followed in September 2013. After careful peer review and cross-analysis, NASA confirmed that Voyager 1 had entered interstellar space in August 2012. For the first time in human history, an instrument built on Earth was operating beyond the heliosphere. The stakes extended far beyond symbolism. The density, pressure, and magnetic behavior of the interstellar medium determine how stellar systems interact with their galactic neighborhoods. They influence the size of astrospheres, the penetration of cosmic radiation, and potentially the long-term habitability of planets orbiting distant stars. Voyager's plasma wave measurement transformed interstellar space from abstraction into data set. The spacecraft was now sampling the raw material between stars. And yet, even in interstellar space, the Sun's magnetic fingerprint had not entirely vanished. The field direction remained curiously aligned with solar expectations. The frontier was not a simple handoff from star to galaxy. It was layered, complex, and Voyager was still moving, deeper into a region where the Sun's influence weakens year by year, and where new measurements would continue to refine our understanding of what it truly means to leave home. Beyond this point lay a broader question. If our Sun's boundary is dynamic and permeable, what does that imply for the countless other stars scattered across the Milky Way? That question carries us forward. By late 2013, Voyager 1 was no longer exploring the solar system. It was sampling the galaxy. After NASA's formal confirmation in September 2013 that the spacecraft had entered interstellar space, attention shifted from crossing the boundary to understanding what lay beyond it. For the first time, direct measurements of the local interstellar medium were available, not from distant spectroscopy, but from in situ instrumentation. The plasma density measured by the plasma wave subsystem remained consistent with interstellar values. Galactic cosmic ray intensity stabilized at elevated levels. The magnetic field strength was stronger than many pre-encounter models had predicted, measuring around 0.5 nanotesla, higher than expected for the surrounding galactic environment. This was the central revelation. Interstellar space near our Sun was not empty and uniform. It was structured, magnetized, and dynamic. The Sun is currently traveling through a region known as the local interstellar cloud, a tenuous, partially ionized cloud of gas spanning roughly 30 light-years. Voyager's measurements provided the first ground truth inside that environment. The density, pressure, and magnetic intensity of this cloud directly determine the size and shape of the heliosphere. In other words, the galaxy itself defines the scale of our solar system's protective bubble. This realization expanded the stakes beyond heliophysics. If the properties of interstellar clouds vary across the Milky Way, then the dimensions of astrospheres around other stars must vary as well. Some stars may possess compact, compressed bubbles under high interstellar pressure. Others may carve expansive cavities in calmer regions of space. The size of that bubble influences radiation exposure for orbiting planets. It modulates the influx of galactic cosmic rays. Over geological timescales, it could affect atmospheric chemistry and mutation rates. Voyager's data suggested that stellar habitability is not determined solely by distance from a star. It is shaped by the galactic neighborhood. The Sun's heliosphere is not fixed. It responds to interstellar conditions that evolve as the solar system moves through the Milky Way at approximately 828,000 kilometers per hour. The boundary we crossed in 2012 is temporary on cosmic timescales. Millions of years ago, the Sun may have traveled through denser clouds. Millions of years from now, it will encounter new ones. Voyager revealed that the solar system is not an isolated island drifting in emptiness. It is immersed in galactic weather. And if our boundary changes with that weather, then every planetary system in the galaxy must experience its own version of this negotiation between star and interstellar space. The question now becomes larger. If boundaries shift, if radiation environments evolve, if stellar bubbles expand and contract over time, what does that mean for life? To answer that, we must look not just at where Voyager is going, but at how long it can continue to send its signal into the dark. In 2023, nearly 46 years after launch, Voyager 1 was still speaking, but its voice was weakening. Powered by a radioisotope thermoelectric generator fueled by plutonium-238, the spacecraft produces less electricity each year as the radioactive material decays. At launch in 1977, the generator supplied roughly 470 watts. By the early 2000s, that output had fallen below 250 watts, and continues to decline. Every instrument operating in interstellar space must now compete for power. Engineers at NASA's Jet Propulsion Laboratory have responded with careful precision. Non-essential systems have been shut down. Heaters have been disabled in subsystems once considered critical. Each year, additional components are powered off to preserve the most scientifically valuable instruments for as long as possible. This is not routine mission management. It is energy triage at the edge of the galaxy. The central discovery of this phase is not about plasma or particles. It is about endurance. Voyager 1 continues to measure galactic cosmic rays, magnetic field strength, and plasma wave activity from more than 24 billion kilometers away. The signal it transmits is only about 23 watts, less than a household refrigerator light bulb. By the time it reaches Earth, it is billions of times weaker than background noise. Yet NASA's Deep Space Network, with its 70-meter radio antennas in California, Spain, and Australia, continues to detect it. Each command takes more than 22 hours to arrive. Each reply requires the same time to return. Communication is measured in days. The stakes are subtle but profound. Voyager is the only operational probe in interstellar space. When its instruments fall silent, projected sometime in the early 2030s, direct measurement of the local interstellar medium will cease. What remains after that will be trajectory alone. The spacecraft will continue outward at roughly 17 kilometers per second, carrying the golden record and the imprint of human engineering into the Milky Way for millions of years. It will not approach another star for approximately 40,000 years. Its scientific mission, however, has a finite horizon. Each watt lost narrows the window of observation. Each subsystem powered down reduces the data returned from beyond the heliosphere. And yet, even as power diminishes, Voyager continues to refine our understanding of galactic space. Subtle variations in cosmic ray intensity reveal how solar cycles propagate outward long after originating at the Sun. The interstellar magnetic field remains aligned in ways that challenge simplified boundary models. The spacecraft is still teaching us, but not indefinitely. Soon, the instruments will fall silent. The last data packet will arrive. The final carrier tone will fade into background noise, and then Voyager will become something else, not a transmitter, not a probe, but a silent ambassador drifting through interstellar darkness. Before that silence comes, however, there is one final question to confront. If our Sun carves out a temporary sanctuary in the galaxy, and if that sanctuary evolves with interstellar conditions, what does that reveal about the long-term future of planetary systems, including our own? That is where our story turns next. The edge of our solar system is not permanent, it moves. Voyager's measurements after 2012 revealed that the heliosphere expands and contracts in response to changes in solar activity and interstellar pressure. This was not speculation. It was supported by particle flux variations recorded across multiple solar cycles and by magnetic field measurements transmitted from more than 120 astronomical units away. The Sun follows an approximately 11-year activity cycle. During periods of high activity, stronger solar wind pushes the heliopause outward. During quieter phases, the boundary contracts. Over decades, the movement is subtle, measured in astronomical units. Over millions of years, it could be dramatic. The solar system itself is not stationary within the Milky Way. It travels through interstellar space at roughly 220 kilometers per second around the galactic center, while simultaneously drifting through localized clouds of gas and dust. Currently, we reside in the local interstellar cloud, a region of relatively low density. Astrophysical models suggest that denser interstellar clouds exist elsewhere in the galaxy. If the Sun were to enter one, the external pressure on the heliosphere would increase significantly. The protective bubble could shrink. Galactic cosmic rays would penetrate more deeply into the inner solar system. The stakes are planetary. Cosmic rays influence atmospheric ionization rates. They can alter cloud microphysics and potentially affect climate patterns. Over geological timescales, increased radiation exposure may influence mutation rates and biological evolution. Voyager's data transform this from theoretical discussion into measurable physics. The heliosphere is not a static shield. It is a responsive boundary, shaped by both stellar output and galactic environment. Its size, at any moment, is the result of pressure balance between solar wind and interstellar medium. In 2018, Voyager 2 crossed the heliopause at approximately 119 astronomical units, providing independent confirmation of the boundary's position in a different direction. The dual measurements reinforced a central truth. The heliosphere is asymmetrical, dynamic, and sensitive to conditions beyond the Sun. This discovery expands the concept of habitability. A planet's environment is influenced not only by its star, but by the star's galactic neighborhood. The Milky Way is not merely a backdrop. It exerts pressure, literally, on every stellar system within it. Our protective bubble is temporary. In hundreds of thousands of years, the Sun will leave the local interstellar cloud. The heliosphere may change in scale and structure. Earth's radiation environment could shift accordingly. Voyager revealed that the edge of our solar system is part of a larger galactic system of flows and fields. The boundary we crossed in 2012 was a moment in time, one frame in an ongoing cosmic evolution. Which leads to the final implication. If boundaries move, if stellar shields change, if galactic weather shapes planetary conditions, then the story of Voyager is not only about where we are, it is about how fragile and contingent our cosmic shelter truly is. And that realization carries us to the final chapter. In September 2013, NASA confirmed that Voyager 1 had entered interstellar space. It was a historic announcement. For the first time, a human-made object was operating beyond the Sun's protective bubble. Yet the deeper discovery was not the crossing itself. It was what the crossing revealed. Voyager showed that the boundary of our solar system is not a wall in space. It is a shifting equilibrium, a balance between outward solar wind and inward galactic pressure. The heliopause is neither permanent nor perfectly defined. It is a dynamic interface shaped by forces on scales far larger than our star. That realization changes perspective. For centuries, the solar system was imagined as a stable architecture, planets orbiting a central sun within a largely empty void. Voyager replaced that image with a different one. The Sun moves through a magnetized, structured galaxy. Interstellar clouds exert pressure. Magnetic fields connect and reconnect. Cosmic radiation flows along invisible corridors. Our planetary system is not isolated. It is immersed. The heliosphere, which shields Earth from a significant fraction of high-energy galactic particles, exists because of a pressure balance that can shift over time. When solar activity rises, the boundary expands. When the Sun weakens or encounters denser interstellar regions, the boundary contracts. On human timescales, these changes are subtle. On cosmic timescales, they may reshape planetary environments. Voyager's instruments, magnetometers, plasma wave detectors, cosmic ray counters, transformed that concept into measurement. They quantified the density of interstellar plasma. They tracked the intensity of galactic radiation. They recorded the strength of the magnetic field that envelopes our star from the outside. The data did not dramatize the galaxy, it normalized it. Interstellar space is not empty silence. It is thin but structured, cold yet dynamic. It exerts influence across billions of kilometers. As Voyager continues outward at roughly 17 kilometers per second, its power supply diminishes. In the early 2030s, its final instruments are expected to fall silent. The Deep Space Network will listen one last time. The carrier tone will fade, but the trajectory will continue. For tens of thousands of years, Voyager will drift between the stars. It will carry a record of human existence through regions whose density and magnetic geometry it was the first to measure directly. The spacecraft did not merely reach the edge of the solar system. It revealed that the edge is part of a larger cosmic system, one in which every star carves out a temporary sanctuary in a dynamic galaxy. The crossing of 2012 was not an ending, it was a redefinition, a reminder that our home is not bounded by a fixed frontier, but by a living boundary shaped by forces beyond our sight. Voyager now travels through that greater ocean, and in doing so, it has expanded the map of human understanding from the scale of planets to the scale of the galaxy itself.